Welcome to the project report. Throughout this series, I'll be sitting down with researchers and highly qualified personnel working on FES-funded research to learn about what it is they're working on, why it matters, and what's to come. So thanks for joining me today, Anil. You're the operations coordinator at Future Energy Systems. How did you get to work with us?
When I was starting my academic journey during my undergraduate days, I had the opportunity to work on energy transitions, and later on when I moved to the University of Alberta for my graduate studies on circular economies for lithium-ion batteries. Again, the core concepts were sustainability and creating a greener future. I had it in mind that all my endeavors should revolve around these aspects. I learned about FES through its outreach efforts. I'm a FES alumni myself. Up to that point in my academic journey, I was focused on the front end of the research aspect. When FES offered me the opportunity as an operations coordinator, it gave me an outlook on the back end of the research spectrum, and I took it with both hands.
So you've had quite the career journey looking at both sides of the research, the front and the back side now. You have researched circular economy and lithium-ion batteries. What does the circular economy framework actually mean, and how does it help solve challenges related to lithium-ion batteries?
Circular economy in general, the framework, is actually quite simple to understand. It essentially means minimizing waste and optimizing the raw materials that go into a production cycle. So the best way to look at it is through the 4 Res: reduce, reuse, recycle, regenerate. So at the start, you have a battery in an electric vehicle. After multiple use, it reaches its end of life. When a car battery reaches its end of life, it does not mean that it is completely extinguished. Around 20% of its capacity has reduced, which means it has around 80% left. That's where the reuse aspect comes into play. So the reuse would be to use it in a second use application where that high levels of capacity are not required. Then comes the other 2 Res that I mentioned: recycle, regenerate. So essentially, after the second use application, you take the raw materials from the battery, feed it back into a second cycle of production. And finally, the reduce aspect, where we minimize our use of the product to prolong its life. This loop where we are reusing the battery for a second use application, we are recycling and regenerating the raw materials for the next production cycle to make the next generation of batteries. This is at heart what a circular economy framework looks like. So as the green transition heats up and as digitalization makes portable devices the norm, we will need more lithium-ion batteries to power it. This leads to challenges that are twofold. The first is the waste management aspect. How do you deal with end-of-life batteries? The second is the logistical side of things. More specifically, as the demand for these batteries increase, so does the corresponding demand for the raw materials needed to make it. And most of this comes from primary extraction and from just a host of geographic regions, which in itself creates challenges down the line. The circular economy framework comes into play to mitigate the effects of these two challenges. So at the core of my research, or my research thesis, was the recycling and regeneration of lithium-ion batteries. At first, I did a literature review to sort of familiarize myself with how this ecosystem works. And I found that there are 3 major methods to recycle and regenerate batteries. And the first 2, or the most common or well-established ones, are called pyro and hydrometallurgy. As the name indicates, these are metallurgical processes that have been repurposed to be used in battery recycling operation. And the third aspect is more of a nascent technology that's been coming up called direct regeneration, where we address the cause of capacity fade, or why a battery degenerates over time, addressing that directly through a non-destructive method. Subsequently, I worked on my experimental aspect, which was sort of making the hydrometallurgical process more effective. So I created an organic acid cocktail, which can effectively recover valuable metals such as lithium and cobalt from a spent battery active material. I achieved almost comparable results to that of mineral acids, which are used as the norm now, but they have a host of disadvantages. I helped optimize and make the recovery process more greener by using less harsh chemicals. By less harsh, I mean less harsh for the environment, and also provide some economic benefits as well.
When it comes to building a greener future, how do you see commercial scale recycling and circular economy frameworks fitting in?
That's an interesting question. So the answer is a bit more nuanced. The perspectives involved is not just that of, say, a researcher. For it to be commercially viable or have a process which is streamlined, what we require is 3 players: academia, which is the researchers themselves, the industry, the ones who will be doing the scale up of the technology that the researchers develop, and policymakers themselves being involved. So it's not a siloed endeavor. You need these three entities to work in unison.
Let's go back to the EV example for a second. Can you explain how the circular economy framework would be best implemented when all of these parties are working together?
Here, the researcher or academia has come up with a technique. But to scale up, industry faces an issue because they cannot make it uniform. The engineering concerns that come into play are feasibility, economic viability, safety, that sort of thing. So if another parameter is added to the start, as encouraged by policymakers, if circularity is introduced at the beginning, the direct regeneration method that I mentioned earlier, that can be utilized. For instance, to make the batteries uniform, they can create modular aspects. And if that is done at the early onset, then recycling can be done like a production chain at the end. So this is where a policy incentive or initiative can help academic researchers scale up their technology to an industrial scale. And this is a very good interplay of the three factors involved. The most prominent one that comes to mind is EPR, Extended Producer Responsibility, which has had quite a bit of success in Europe. So what it entails is that producers bear the responsibility of recycling their products. And if you want to give a battery example, so if a manufacturer makes 1,000 batteries, they could be mandated by a government that they should recycle at least 50% of it. So they have to recycle 500 of it. This has been quite successful because the producers themselves bear the responsibility of recycling the batteries that they manufacture. Even in some instances, it doesn't have to be their own product. It could be from another company producing batteries, as long as they bear the responsibility of the recycling aspects. The circularity aspect or circular economy framework is not limited to that of batteries or battery production. Literally, any aspect can be fitted into the circular economy framework. My research has sort of evolved in that direction. The recycling of photovoltaic cells and how that fits into a circular economy framework. I've also had the opportunity to work on the production of syngas from municipal solid waste, MSW. All of these fall under the circular economy framework. So that's one thing I want to emphasize. And my research trajectory is going in that direction at the moment. I believe that engineering training, at least, we are always dealing with technical feasibility, economic parameters, safety, reliability, that sort of thing. So these are the tenets for success that are given to us. And another parameter that should be indispensable should be that of the circularity aspect of production. So when that mentality is instilled right from the start to the end, circular economy frameworks will obviously follow. The interplay that I mentioned between the three entities, they can be optimized through this sort of thinking.
Some of your work was also recently published. Where can people find those publications?
They can be found in my Google Scholar page, also in the research websites of my supervisors, Dr. Zhaoli Wong from the University of Alberta and Dr. Anil Vinayak from Vellore Institute of Technology. My mentors their inputs were quite invaluable. And also I would like to thank the institutional support provided by the University of Alberta and Vellore Institute of Technology. Of course, it would not have been possible without the support of my supervisors. And finally, and maybe even most importantly, I want to thank Future Energy System for the opportunities they have provided and helping me conduct my research, as well as giving me the opportunity to work on all aspects of the research ecosystem.
Yeah, well, from circular economy framework to lithium-ion battery recycling methods, your research has clearly done a lot to contributing to a greener future. So thank you so much for sharing everything with me today.
It was my pleasure.